We all remember 1969, the moon landing. Truly a landmark moment.
Absolutely.
Iconic. But, while those first steps were huge, our actual deep understanding of the moon, that's really blossomed in the decades since.
That's right. The Apollo missions brought back those invaluable samples, the moon rocks.
But it's the robotic missions that followed. They've painted a much richer picture.
Definitely. So the real question for us today, I think, is what have we fundamentally learned about the moon since we last walked on it back in '72?
Exactly.
So in this deep dive, we'll try to synthesize findings from, analyzing those Apollo rocks and combine that with data from more recent missions.
We're talking NASA, Smithsonian analysis, but also international efforts, right?
Yes, absolutely. China's Chang'e missions have been groundbreaking, and India's Chandrayaan program, too. Crucial contributions.
The goal here is really to give you a clear, concise graph of where our lunar knowledge stands now, post-Apollo.
A shortcut, if you will, to being up to speed on lunar science.
We'll touch on how the moon formed, how it evolved, what that dust is really like.
And the challenges for humans going back, plus the whole hunt for resources, especially water.
Okay, let's dive in. Starting with those moon rocks. What secrets did they unlock first?
Well, one of the biggest was the moon's age. By analyzing tiny zircon fragments in those rocks.
Zircon, okay.
Scientists were able to pin down its formation to about 4.5 billion years ago.
Which really supports the giant impact idea, doesn't it?
It does. The theory that the moon formed from debris after something massive or maybe a series of things hit the early Earth. All that ejected material eventually came together.
So it wasn't just sort of formed alongside Earth as a companion.
Doesn't look like it.
Yeah.
And the rocks also showed the moon isn't some static primordial relic.
Ah, right. It's evolved.
It's an evolved terrestrial body. It's gone through significant geological changes, melting, massive meteorite impacts, even volcanism.
A whole history written in those rocks.
Precisely. It's had a dynamic past.
Amazing. Now, what about life? That was a huge question early on. Did we find anything?
The answer there is pretty definitive, based on everything we've seen so far.
Which is?
Lifeless.
Yes.
Rigorous checks, the Apollo samples, data from landers. There's just no evidence of past or present life. No fossils, no native biological compounds.
But some organic compounds were found.
Yes, but they're non-biological. The conclusion is they came from meteorite impacts contaminating the surface. So as of now, the moon is a lifeless world.
Stark. Okay, let's shift to something very tangible for anyone going there. The dust. That lunar regolith. What have we learned about it?
Ah, the regolith. It's everywhere. Chemically, about half of it is silicon dioxide, sort of like sand on Earth.
Okay.
The rest is a mix of metal oxides. Aluminum, calcium, magnesium, titanium, and iron.
And the iron is different there, isn't it?
Yes, it's mostly in its reduced metallic state.
Yeah.
Seated form, not oxidized like rust, because there's virtually no atmosphere or free oxygen.
Yeah.
And that affects its properties quite a bit.
And the shape of the dust grains themselves, I gather they're not smooth.
Far from it. Micrometeoroid impacts and solar wind sputtering are the main sculptors.
Solar wind sputtering, that's the wind knocking atoms off.
Essentially, yes. It creates these grains that are often elongated, really angular, sharp edges, very irregular surfaces.
You also see these little glass bits stuck to them.
Exactly. Tiny mounds of glass from impact melt that splashed onto existing grains and solidified. Very different from the rounded grains you might find shaped by wind and water on Earth.
So a very abrasive environment on a tiny scale.
Definitely. And within that regolith, you find different particle types too. Glassy beads from melt cooling quickly, angular shards, basically broken glass fragments, vesicular particles, kind of porous ones.
Porous.
Likely from trapped solar wind gases escaping as they formed. Then you have aggregated particles, smaller bits stuck to larger ones, and just blocky fragments of rock and minerals.
Each telling a bit of the story of the surface processes.
That's the idea. They give clues about the impact history and other lunar processes.
Now, you mentioned the iron. There's something special about it at the nanoscale, right? Nanophasic iron.
Correct. Especially in the finer dust, you find these tiny nanometer-sized droplets of metallic iron, MPF.
And why is that significant?
Well, it makes the dust more chemically reactive. It also gives it specific magnetic properties and affects how it interacts with microwaves.
Which could be useful.
Potentially, yes. Maybe for dust removal systems that use magnets, for example.
Okay, and this brings us squarely to the health hazards for astronauts. This dust is a major concern.
It absolutely is. A lot of this dust is incredibly fine. We're talking particles smaller than 10 micrometers and even ultrafine, less than zero point 0.1 micrometers.
And those are the ones that get deep into the lungs.
Exactly. They can bypass the body's upper airway defenses and reach the deepest parts, the alveoli, where gas exchange happens.
And they don't get cleared out easily.
No, the body's clearance mechanisms are much slower for these fine particles. It can take days, even months. The ultrafine ones might even get into the bloodstream.
Which increases the risk.
It increases the potential toxicity, yes, because they stay longer and can potentially travel further.
So what specific health problems are we talking about? Based on lab studies, presumably.
Right, using lunar dust simulants. Research points to risks like oxidative stress damage at the cellular level and DNA damage in lung cells.
Which can lead to inflammation.
Yes, inflammation and potentially pulmonary fibrosis, that's scarring of the lung tissue. Studies also show it can affect lung immune cells, macrophages, possibly making them more inflammatory and less effective.
A serious respiratory threat. What about other parts of the body?
Well, based on studies of terrestrial air pollution, there's concern about cardiovascular effects.
How so?
If these ultrafine particles get into the bloodstream, they could potentially trigger inflammation and oxidative stress systemically, which are known risk factors for heart disease. It's a plausible link, though more research specifically on lunar dust is needed.
A worrying possibility. And skin and eyes are vulnerable too.
Yes. The dust is abrasive, it clings. So skin irritation, abrasions, potentially slowed wound healing. Lab studies on skin cells showed some toxic effects and impaired healing.
And eyes.
Obvious risk of irritation, corneal abrasion if it gets in the eyes.
You also mentioned potential neurological effects.
That's an emerging area. One study found a strange interaction with glutamate binding at nerve endings. Plus, there's the theoretical possibility, seen in some animal studies with nanoparticles, that they could potentially reach the brain.
Wow. It really drives home how challenging that environment is. Dust isn't just a nuisance, it's a significant health risk.
Absolutely. And the Apollo astronauts did report some minor issues. Sneezing, eye irritation. It highlighted the need for really good dust mitigation.
Which brings us to the more recent missions. The Lunar Reconnaissance Orbiter, LRO, has been pivotal.
Hugely important. It gave us that incredible high-resolution 3D map of the entire moon.
Which is essential for planning future missions, finding landing sites.
Understanding the terrain, identifying resources, absolutely. Then there's the Artemis spacecraft part of the program to return humans, but also gathering key data on the solar wind around the moon.
And we have to talk about the international missions. China's Chang'e program has had some major successes.
Definitely. Chang'e 4, the first ever soft landing on the far side. A huge achievement.
In the Von Karman crater, right. Within that massive South Pole Aitken Basin.
Exactly. A scientifically fascinating area, potentially holding clues to the moon's early history and deep crust.
Landing on the far side must be incredibly complex.
Oh, absolutely. The terrain is rugged, so you need very sophisticated guidance and control. And of course, you can't communicate directly.
You need a relay.
Right. The Quechua satellite was essential for that communication link back to Earth.
And the far side is special for science, too, particularly radio astronomy.
Yes, because it's shielded from Earth's radio noise. It's an incredibly quiet place to listen for faint, low-frequency signals from the early universe.
Like studying the cosmic dark ages.
Precisely. The NCLE instrument on Quechua is aiming to do just that, listen for signals from before the first stars formed, using the moon as an observatory.
Incredible. Chang'e 4 also measured radiation, didn't it?
It did. First comprehensive measurements from the surface. And it confirmed radiation levels are significantly higher than on the ISS or even during airline flights.
Which means shielding for astronauts is critical.
Absolutely paramount for long-duration stays or extensive surface activities.
Now, what about that gel-like substance the U-22 rover found? That caused a bit of a stir.
It certainly did. The initial description, dark greenish glistening, was intriguing.
But it turned out to be something more familiar.
Yes. After analysis, it was identified as impact melt breccia. Basically, rock formed when an impact melts and fuses together bits of regolith. Similar samples were actually found by Apollo.
So, not alien goo, but still informative about impacts. Did U-22 analyze the soil too?
Yes, with its spectrometer. It found the soil in its landing area seems to be mostly weathered neritic rock, possibly originating as ejecta from the nearby Finsen crater. Helps piece together the local geology.
Okay, let's move to India's Chandrayaan-3, another mission focused on the South Polar region.
Yes, another successful landing near the South Pole. A prime target because of the potential for water ice.
And its rover, Pragyan, had instruments for analyzing the soil right there.
Right. LIVIS's laser-induced breakdown spectroscopy and APXS, an X-ray spectrometer, both designed for in situ elemental analysis.
And they found
A really significant confirmation: unequivocal detection of sulfur near the South Pole.
Why was that important?
Because detecting sulfur definitively from orbit is difficult. This ground truth was key. They also confirmed other expected elements: aluminum, calcium, iron, silicon, oxygen, and others.
And the search for hydrogen, for water, is ongoing.
Correct. That's still being analyzed.
Which leads us nicely to the whole water on the moon story. That's changed dramatically since Apollo, hasn't it?
Oh, completely. The Apollo samples looked extremely dry, suggesting an anhydrous moon.
But 21st century missions tell a different story.
Absolutely. Missions like Deep Impact, Japan's Kaguya, India's Chandrayaan-1, NASA's LRO, even the Sophia Airborne Observatory, they've all provided evidence for water.
In what forms?
We now think there's water ice, likely mixed with soil, in those permanently shadowed craters at the poles.
Where it's incredibly cold.
Permanently frozen. We've also detected water molecules in the moon's very thin atmosphere, its exosphere, and even traces on the sunlit surface, which was a surprise.
So not vast underground oceans, but ice mixed in the regolith.
That seems to be the picture. Probably small grains or crystals in the top layer of soil, and some water might be chemically bound within minerals too.
And these permanently shadowed regions act as cold traps.
Exactly. Water vapor moving across the surface can get trapped and frozen there. And interestingly, recent work suggests there are many smaller micro-cold traps too, which could mean ice is more widespread in polar regions than we thought.
That increases the potential resource quite a bit. What about water from deep inside the moon?
Well, analysis of those volcanic glass beads from Apollo did find water molecules trapped inside,
Suggesting the lunar interior wasn't always dry?
suggesting it might have been significantly wetter during its volcanic past. But that water isn't easily accessible. It came from deep down.
But the ice at the poles, that's the game changer for future exploration.
Huge potential. Water for life support, obviously. But also you can split it into hydrogen and oxygen rocket fuel.
Making the moon a potential refueling star.
Exactly. A stepping stone for missions further out into the solar system. It could transform space exploration economics.
But living and working there means dealing with that dust. What technologies are being developed for mitigation?
A lot of work is going into that.
Well,
Broadly, active and passive methods.
active being, removing dust.
Right. Things like vibrating surfaces, blowing gas, using brushes, maybe those magnetic rollers we mentioned.
Fast.
Designing things to be dust tolerant from the start. Smooth surfaces, materials that dust doesn't stick to well, seals that keep it out.
What about the spacesuits themselves? Apollo suits got pretty dusty.
Yeah, big improvements are needed. New suits are looking at pressurized systems to keep dust away from the skin and advanced materials that actively repel dust.
Like that spike gear concept with an electric field.
Exactly. Generating a charge on the suit surface to push away the charged dust particles. Still experimental, but promising.
And power. The long, cold lunar night is a challenge for solar panels.
It is, especially near the poles. One interesting option being developed is nanotritium batteries.
Nuclear batteries.
Essentially, yes. Tiny ones using the radioactive decay of tritium, an isotope of hydrogen, to generate power continuously. They're durable, long-lasting, and work well in extreme temperatures and radiation.
And tritium was used in the Apollo watches.
For illumination, yes. A nice little historical connection there.
So, pulling all this together, are there lessons from all this lunar research that help us plan for Mars?
Definitely. While Martian dust is different, it has things like perchlorates, different mineralogy.
But some similarities.
Yes, like the electrostatic charging. But fundamentally, learning how to deal with lunar dust toxicity, developing mitigation techniques, improving radiation, shielding all that experience is directly relevant to Mars.
Understanding how to operate safely in one dusty, harsh environment helps prepare for another.
Precisely. The moon is an invaluable testbed for technologies and procedures we'll need on Mars.
So, wrapping up, it's fair to say our view of the moon has been completely revolutionized since Apollo.
Absolutely. We've gone from seeing it as mostly static and dead to understanding its dynamic past, the hazards of its dust, the unexpected presence of water.
And we're developing the tech to go back and stay longer.
The moon today looks far more complex, more active in its history, and potentially more resource-rich than anyone imagined in 1969.
So, the final thought perhaps is this. With this dramatically new picture and with this renewed push for human missions, What discoveries are still waiting for us? What unforeseen insights will we gain when we return? And how will they change our understanding not just of the moon, but of Earth and our place in the cosmos?
A tantalizing question.
Yeah,
There's still so much to learn.
indeed. We really hope this deep dive has given you a solid grasp of where we stand. We encourage you, if something caught your interest, Artemis, Chang'e lunar dust science, dig a little deeper. The story is far from over.